So, if we go back to 1996, the European Space Agency launched the Ariane 5 rocket.
Oh, right. The infamous Ariane 5 launch.
Yeah, infamous is the right word. I mean, 37 seconds after liftoff, the entire vehicle it abruptly veered entirely off its flight path.
Right, and the aerodynamic strain at that speed is just, well, it's immense.
Exactly. It broke apart under the strain, and that triggered its automatic self-destruct sequence. So you have $370 million plus, years and years of scientific payloads just vaporized over the coast of French Guiana.
It's just staggering to think about.
It really is. And the craziest part, to me at least, is that the culprit wasn't like a faulty thruster or some kind of fuel leak.
No, it was a software issue, strictly code.
Right. It was a single piece of unprotected code. And it was just trying to stuff a 64-bit floating point number into a 16-bit physical register.
Which is physically impossible. You literally cannot fit that much data into that small of a physical space on the chip.
Right, caused an integer overflow. And because this was what we call a bare metal embedded system, meaning it didn't have the safety nets of like a normal commercial operating system, the entire inertial reference system just folded.
Yeah, it basically threw its hands up. I mean, the physical hardware faithfully executed a mathematical impossibility, and, well, gravity did the rest.
Gravity always wins in the end.
It really does. And, when you're writing code for bare metal microcontrollers, there is no judge to evaluate the legality of your request. You know what I mean? There's only the executioner.
Wow, only the executioner. That's kind of a dark way to look at it.
But it's true. The processor simply attempts whatever binary instruction is fed into it, regardless of the physical reality of the registers or the catastrophic downstream effects.
And that terrifying lack of a safety net is exactly what we were unpacking today in this deep dive. We're going to explore this meticulous, incredibly unforgiving world of physical chip testing and verification.
It's a world most people don't even know exists, honestly.
Right. And our sources today detail this really revolutionary verification protocol. It's called a candidate test gate.
Yeah, the candidate test gate. It's an amazing concept.
It is. It's a system designed specifically to verify embedded code on real physical silicon. But I think what makes this genuinely fascinating, like the real hook here, is the ecosystem around it.
Right, because we aren't just talking about modern, trendy software here.
Exactly. We're looking at bringing uncompromising, thoroughly modern verification to the fourth programming language, which is, a 50-year-old architectural marvel.
It's 50 years old and still running critical systems all over the world.
Yeah, and they're doing this using an unprecedented pair programming partnership. It's a team up between a veteran human electronics technician and a high-speed artificial intelligence.
Which is just the ultimate odd couple pairing, right? You've got legacy expertise meeting cutting-edge AI.
It really is. But before we get to the AI, we are focusing on Forth because of its really unique footprint. I mean, Charles Moore developed Forth in, the early 1970s?
Mm-hmm. Yeah, early 70s. And he developed it specifically to control radio telescopes at the National Radio Astronomy Observatory.
Right, which meant it had to be incredibly efficient.
Extremely efficient. It is so close to the hardware. It's incredibly memory efficient. And because of that, it has been the sort of silent engine behind decades of embedded systems.
I mean, it ran the FedEx handheld trackers in the 80s, right?
Oh, yeah. And it's heavily utilized in automotive controllers today. And my favorite example, it famously traveled on the Philae lander that actually touched down on Comet 67P.
Which is mind-blowing, but that proximity to the hardware, the fact that it's so close to the bare metal, means the stakes are just incredibly high.
Oh, absolutely. When you're that close to the metal, a single transposed hex code doesn't just, crash a browser tab like it would on a laptop.
Right. You don't just get a little sad face icon and reload the page.
No, you don't. It corrupts the fundamental physical state of the silicon itself.
And to really grasp the gravity of this candidate test gate system we're talking about, I think we have to look at the massive psychological shift required when you move from traditional software development to embedded bare metal.
It's a completely different mindset. Most developers today, they operate in a sandbox.
Yeah, exactly. You sit at your PC, you compile a function, and if you accidentally misallocate memory, well, the operating system intervenes.
Right. The OS steps in like a chaperone. You get a segmentation fault, maybe a polite error message on your screen, and you just go debug it.
The operating system acts as a hypervisor. It's completely abstracting away all the messy physical realities of the machine.
And that abstraction is a luxury, right? But it's a luxury that breeds complacency.
How so?
Well, I mean, we all know what a register is from, like Computer Science 101. But in standard desktop development, we just treat registers as infinite mathematical variables.
Right, they're just abstract buckets we throw numbers into.
Exactly. But in the bare metal embedded context, we have to stop thinking of registers as math, and we have to start thinking of them as physics.
Physics. Okay, so unpack that for someone who might be new to this. What is a register, really, in the physical sense?
Okay, so a register is a microscopic physical latch, literally carved into a silicon die. When your fourth code executes, it is directing the microcontroller to route raw physical electrical voltage into those specific latches.
Real electricity moving into real microscopic switches.
Yes. And there is no middle manager. There's no OS to say, hey, wait a minute. If you tell the processor to write data to a memory address that, say, governs the watchdog timer instead of the general purpose memory, the processor just complies.
It just blindly does it. Because the concept of, like, access denied requires a layer of software to enforce it, right?
Precisely. On bare metal, you are the CEO setting the strategy, but you're also the machinery operator pulling the actual levers simultaneously.
That's a great way to put it. Which brings us to the core risk identified in our sources, and I think this is fascinating, silent corruption.
Oh, silent corruption is the absolute worst-case scenario in embedded systems.
Because a loud failure, like a hard fault where the processor completely halts and catches fire, that's actually the best-case scenario, right?
Counterintuitively, yes, because at least you know something is broken. You can go fix it. Silent corruption is the real nightmare because you're flying blind.
Let's analyze that. Let's look at the mechanics of a complex register corruption scenario to see why it's so insidious. Give me an example of what this actually looked like in the real world.
Sure. Okay, so imagine a commercial embedded system. Let's say it's the microcontroller governing a medical infusion pump in an ICU.
Okay, very high stakes.
The highest. Now, the code utilizes a specific hardware timer register to calculate the drip rate of a really powerful sedative.
Got it. So there's a physical timer tracking the drips.
Right. Now, suppose a poorly verified fourth word, and remember, a fourth word is essentially just a subroutine or a specific command in the language. Suppose this word has a really subtle bug.
Like what kind of bug?
Well, let's say it is supposed to clear register A, right? But due to an off-by-one error in the physical memory mapping, it accidentally flips a single bit in register B.
Oh, no. And register B happens to be our drip rate timer for the sedative.
Exactly. And the really scary part? The system doesn't crash.
Because structurally, I guess nothing illegal happened.
Exactly. The memory address was technically valid, and the physical voltage was successfully applied to the latch. The hardware did exactly what the code told it to do.
It just had no idea that what the code told it to do was completely wrong for the patient.
Precisely. The microcontroller doesn't know the mathematical intent of that voltage. It just knows it successfully toggled the latch. So the pump continues operating.
And the digital display on the pump.
The display might look perfectly normal, especially if the user interface is running on a completely separate thread or querying a different, cached variable.
So no alarms sound, no telemetry alerts are fired to the nurse's station.
None. But the actual physical drip rate has been subtly accelerated. The patient begins receiving an overdose, and the internal logs would technically show the machine functioning flawlessly.
That's horrifying. So a patient could literally be overdosed. And a post-mortem analysis of the digital logs by the hospital might completely miss the hardware-level discrepancy because the software truly thought it was doing the right thing.
Yes. And that right there, that shifts the entire paradigm of how we have to test these systems.
It's like testing on a PC is like flying a flight simulator, right? If you crash, you just hit reset, no big deal.
Right, nobody gets hurt.
But testing on bare metal is like flying a real plane. If you mess up a physical switch, the engine actually shuts off midair. So we can't just test the software logic in isolation anymore.
No, not at all. We have to demand physical proof from the hardware itself. We basically have to prove that the atoms on the chip perfectly align with our human intent.
Which perfectly transitions us to the first phase of the candidate test gate outlined in our sources. Because every single embedded fourth word must pass through this gauntlet before it is accepted into the primary language server for production use.
It's a very strict toll booth.
Yeah, but here's the thing that really surprised me. Before we get to the voltage and the silicon and the cool hardware stuff, the gate enforces an incredibly strict human-readable documentation check.
Right. It mandates a formalized design document, a plain text explanation, and what is known as a stack comment.
Okay, wait. I have to push back on this. We're building this uncompromising bare metal hardware verification loop, and step one is grading an English essay.
I know, it sounds a bit analog, doesn't it?
It seems incredibly unscientific.
Yeah.
I mean, if the ultimate goal is mathematically proving the state of microscopic silicon latches, why involve human semantics at all? Humans are messy, we're ambiguous, we're imprecise. Why not bypass the human language entirely and just jump straight to the math and the hardware behavior?
It's a fair question, but here's the fundamental issue. Without human semantics, you have absolutely no ground truth.
No ground truth. What do you mean?
Look, hardware is deterministic. It will execute a completely flawed instruction with absolute terrifying perfection.
Right, like the ICU pump. It perfected the overdose.
Exactly. So if you jump straight to the silicon, you can hook up all your fancy logic analyzers, and you can verify that the chip took the integer 5, added the integer 3, and correctly stored the integer 8 in the target register.
Okay, so you've proven the physical mechanics of the addition worked.
Yes, you've proven the addition. But how do you know the application wasn't actually supposed to multiply them?
Ah. Oh, wow. I see. The hardware is completely blind to its own purpose.
It is entirely blind. It only knows execution. You cannot verify a system if you lack a baseline definition of correctness. And that is exactly what the documentation phase provides. It establishes the unyielding baseline intent.
So it's like a contract.
Exactly. And in fourth, this is actually deeply embedded in the language's architecture through something called the stack comment.
Okay, let's break that down for the listeners. What exactly is a stack comment in fourth?
So fourth is a stack-based language. It often uses what's called reverse Polish notation.
Which sounds intimidating, but it just means the order of operations is different, right?
Right. Instead of writing A plus B like you would in normal math, you push A onto the data stack, then you push B onto the stack, and then you call the add word to act on whatever is on top of the stack.
Okay, so you line up the ingredients first, and then you apply the action.
Exactly. And the stack comment is a formalized notation that describes this. It usually looks something like a parenthesis, then the input parameters, a double dash, and then the output parameters, followed by a closing parenthesis.
So, for example, it might look like N1, N2 sum.
Yes, exactly that. It explicitly tells the next developer, and more importantly, the testing system, exactly what the stack should look like before the word executes and what it absolutely must look like after.
So that stack comment and the design explanation, they really do act as an immutable contract.
They are the ultimate contract. It's an agreement between the human programmer, the compiler, and the eventual bare metal verification suite.
And if that contract is flawed right out of the gate, say the text says the word calculates an average, but the stack comment shows it only takes one input integer.
Then the candidate test gate rejects it immediately. Bam! Try again. There is absolutely no point in firing up the physical silicon if the human intent is logically or mathematically incoherent.
That makes total sense. You have to know what you're looking for before you start looking.
Right. Only once that conceptual foundation is flawless do we move to the physical realm.
And this transition to the physical realm is where standard testing protocols usually start to fall apart, right? Because we want to know exactly what the microcontroller is doing. But observing a microchip at runtime presents almost like a Heisenberg-like observer effect.
Oh, the observer effect is huge in embedded testing.
Because the moment you introduce standard debugging software to watch the processor, you are fundamentally altering the processor's state, aren't you?
You are. You're consuming precious clock cycles, you're taking up memory bandwidth, and you are potentially masking the very timing bugs you're trying to find in the first place.
So if we need absolute proof without altering the system, why not just use a really highly advanced software simulator? Like, why bother with the physical chip at all if it's so friendly to observe?
Well, simulators are vital, don't get me wrong. We use them for early stage development all the time. But they represent a deeply sanitized, idealized version of reality.
Sanitize how?
A simulator is basically just a software model based on the manufacturer's architectural blueprints. It assumes perfect voltage, perfect clock stability, and flawless logical execution every single time.
But the real world isn't perfect.
Far from it. Physical silicon is chaotic. It is subject to thermal drift as it heats up, parasitic capacitance on the microscopic traces, electromagnetic interference from outside sources.
It's the messy physics of the real world. Like, a zero isn't really a perfectly mathematically zero, is it? It's just a physical voltage level that falls below a certain threshold.
Yeah.
And a 1 is a voltage above another threshold.
Exactly. And between those two thresholds is a sort of dead zone where logic completely breaks down. Furthermore, simulators almost universally fail to account for what the industry calls silicon errata.
Silicon errata, that's the industry's very polite euphemism for hardware bugs that accidentally made it through the multi-million-dollar fabrication plan, right?
It sounds so much better than factory defect, doesn't it? But yes, it is an unavoidable reality of semiconductor manufacturing. Every complex microcontroller on the market has known documented flaws in its physical design.
Really? Like
Yeah.
brand new chips shipped with physical bugs?
Oh, absolutely. Hundreds of them sometimes. These are usually edge cases where, for example, if you trigger a direct memory access transfer at the exact nanosecond a specific interrupt fires, the internal hardware bus might just drop a byte of data.
Just lose it into the ether.
Yep. And a simulator will never catch this because the simulator's logic model doesn't include the physical flaw. The simulator assumes the manufacturer designed the bus perfectly correctly.
So testing on a simulator is essentially like testing the aerodynamic properties of an airplane design in a computer program, while completely ignoring the fact that the actual factory built the left wing a millimeter too short.
That's a perfect analogy. If you want to find the real bugs, the physical bugs, you have to fly the physical plane.
Which brings us to the second phase of the candidate test gate's execution loop. The system takes that human-verified fourth word, compiles it into raw machine code, and executes it on the actual physical target microcontroller.
Right, on the bare metal itself.
But execution is only half the battle, as we established with the observer effect. How do we verify the execution was correct without introducing that Heisenberg problem?
This is where the gate methodology gets really, really clever.
Our sources detailed this brilliant mechanism called native disassembly. Once the code is executed, the gate doesn't rely on an external PC to read the memory and interpret what happened. It actually forces the chip to use its own native disassembler to read its own memory.
And this is such a crucial distinction in building what we call a chain of trust. When we compile forth into machine code, it becomes a sequence of raw binary instructions, right? Ones and zeros.
Right.
To verify that the compiler didn't make a mistake or that some random memory bus error didn't mangle the code during the transfer to the chip, we have to reverse the process. We have to disassemble the binary back into human-readable assembly language.
But normally, developers would just extract that binary dump via like a JTAG debugging cable and then run it through a disassembler on their big fancy Windows or Linux machine, right?
Yes, that's standard practice. But the moment you do that, you've just introduced a massive external dependency into your chain of trust.
You've introduced a third-party translator.
Yeah.
Exactly. If the external software on your PC has a parsing bug, it might report that the machine code on the chip is perfectly fine when, in physical fact, the silicon is holding a corrupted instruction.
It's like asking a suspect to administer their own polygraph test versus relying on a translator who might completely misinterpret the suspect's dialect.
I love that. By forcing the target chip to natively disassemble its own memory, you are interrogating the silicon directly. You're basically asking the physical processor, hey, read your own microscopic latches, use your own internal logic, and output the exact assembly instructions you are currently storing.
It just completely strips away the intermediary. The chip is testifying against itself.
Yes, and doing it natively means if the memory is corrupted, the chip itself will report the corrupted instruction.
But even that isn't enough for this candidate test gate, because let's say the native disassembly proves the instruction sitting in memory is totally correct. The chip knows it needs to execute an addition. We still have that silent corruption problem. Did the final result of that addition actually land in the correct physical register without a random bit flipping along the way?
Right, the landing is what matters.
And this is where the third and fourth steps of the execution loop come in. Writing the result to a specific physical register, and then conducting a completely independent readback.
And this right here is how professional embedded systems engineers verify register states with actual mathematical certainty.
Walk us through it.
So in our daily coding, lives on a PC, we assume that when we type, x equals 5, the variable x securely holds the value 5. End of story.
We trust the system.
Right. But on bare metal, we must pull the latches. We trust nothing. So the candidate test gate configures the fourth word to output its final calculation into a highly specific hardware register. Let's just say general purpose register 4.
Okay, register 4. The fourth word does its math. It finishes, and it drops the result into register 4.
The word executes. And then, rather than asking the fourth word if it succeeded...
Because the fourth word might lie if it's broken, right?
Exactly. The testing harness uses a completely separate, independent diagnostic pathway. Maybe a dedicated hardware debugging probe, or an isolated hardware macro to interrogate register 4 from the outside.
It's like mailing a letter, but instead of trusting the postal tracking app that says delivered, you physically drive to the destination to look inside the recipient's actual mailbox to see the envelope.
That is exactly what it is. It independently queries the physical voltage state of that specific location on the silicon die.
Give me an example of what it's looking for.
Sure. If the fourth word was supposed to write the hex value FFFF, which in binary is a full row of ones,
Okay, all ones.
the independent readback mechanism must return FFFF. If it queries the physical latch and it returns FFFE, we know instantly that the lowest physical bit failed to flip.
Wow. We've captured silent corruption right in the act.
We caught it red-handed. The logical intent was perfectly correct, the instruction in memory was correct, but the physical reality failed to execute.
When you lay it out like that, taking the time for compiling, executing on real silicon, doing a native disassembly, doing targeted register writes, and then doing independent hardware readbacks for every single word in the language vocabulary, the sheer scale of this operation becomes apparent.
It is massive.
This isn't just optimizing your daily embedded verification routines. This is an obsessive, exhaustive interrogation of the physical layer.
Obsessive is a good word for it. It is an incredibly resource-intensive protocol. Implementing this verification checklist across a complete production-ready language server generates a staggering volume of data.
I can only imagine.
You are producing thousands and thousands of native disassemblies, constant physical memory state bumps, and just endless streams of register validation telemetry.
And a human engineer cannot process this at scale. If you hand a master technician 10,000 lines of hex dumps and say, hey, go find the one flipped bit that indicates a microsecond timing erratum, they'd go crazy. It would take months.
Months if they found it at all. It's looking for a needle in a digital haystack.
Which brings us to the real bottleneck of this whole operation. Because if we are independently polling physical registers for every single micro instruction, the bottleneck isn't the speed of the silicon anymore, and it isn't the testing harness itself.
No, the bottleneck is the human trying to read the matrix.
Exactly. How do you possibly scale that? And this is where the source material unveils what I think is the most purely fascinating aspect of this entire project, the ultimate pair programming team.
The human-AI collaboration, it really is the secret sauce here.
Let's get into this. To manage this unprecedented influx of physical telemetry, the project pairs a 72-year-old electronics technician, a veteran with over a decade of deep, highly specialized fourth experience, with a high-speed artificial intelligence specifically trained to ingest and analyze bare metal disassemblies.
It's just a brilliant approach to solving the bottleneck.
Let's talk about the human side of this first, because the demographic detail here, the fact that this technician is 72 years old, I think is vital context.
I agree. It changes the whole dynamic.
A 72-year-old electronics technician possesses a completely different paradigm of computing than, say, a 22-year-old recent computer science graduate.
Night and day difference.
This is someone whose career likely predates widespread internet access, someone who learned to debug hardware using actual analog oscilloscopes and those old logic analyzers the size of filing cabinets.
Right. They possess what we call tacit knowledge.
Tacit knowledge. Tell me more about that.
So, in the world of legacy embedded systems, there is this immense repository of intuition that is never, ever formalized in a manufacturer's official datasheet.
Stuff you only learn by getting your hands dirty.
Exactly. A technician with that level of tenure just intrinsically understands the esoteric behaviors of hardware. They know, for example, that a specific older family of microcontrollers tends to experience weird voltage sags when the internal flash memory is erased too quickly.
Something the manual would never warn you about.
Never. And they understand the philosophical architecture of Forth itself, why Charles Moore designed the vocabulary to function as a cooperative ecosystem of small words rather than a rigid top-down hierarchy.
They are like the master mechanic who can just listen to the rhythmic tapping of a car engine and immediately identify a sticky intake valve without ever plugging in an OBD software scanner.
That's spot on. They have an intuitive, almost instinctual map of the physics. But their biological limitation, unfortunately, is bandwidth.
Right. A human simply cannot read a gigabyte of hex dumps in real time, no matter how much intuition they have.
Which is precisely where the AI becomes indispensable.
We really need to look closely at the mechanics of this artificial intelligence because it is not acting as a generic conversational chatbot here.
No, it's not writing emails or summarizing PDFs.
Right. It operates as a highly specialized pattern recognition engine built specifically for the incredibly dense data pipeline of machine code.
Right. The AI ingests this continuous, blazing fast stream of native chip disassemblies, and it tokenizes the machine instructions.
Breaking them down into digestible patterns.
Exactly. It essentially builds a vast, hyper-detailed statistical model of what correct physical execution should look like, based entirely on the human's documented intent.
Oh, tying it back to the documentation. So the AI is essentially cross-referencing the ground truth, that English essay and the stat comment from phase 1 against the actual native hex dump pulled directly from the physical silicon.
Precisely. It uses advanced sequence-to-sequence modeling to compare the expected architectural flow against the microscopic reality.
Give me an example of how that works in practice.
So, if the human technician dictates in the design phase that a specific fourth word should require exactly 12 clock cycles and interact with only 3 specific registers,
Okay, that's the baseline rule.
the AI just sits there and monitors the incoming telemetry. And if it detects a disassembly graph that suddenly utilizes an undocumented microinstruction, or if it spots a register state that diverges from the expected physical voltage map by even a single bit,
It instantly flags the anomaly.
instantly it flags it for the human to review.
It really is the ultimate forensic laboratory, isn't it? I mean, the human detective has the street smarts, the deep understanding of motives, and the knowledge of how the system should operate in the real world.
And the AI.
The AI is the mass spectrometer that can process 10,000 DNA samples in 5 seconds to find the one microscopic trace of evidence that doesn't belong.
That's a great analogy. And this collaboration completely redefines the evolution of forth testing. And frankly, I think it redefines the testing of commercial embedded systems at large.
How so? Like looking at the historical context.
Yeah, if we trace the legacy of hardware verification, say 30 or 40 years ago, the standard was almost purely functional.
Functional meaning, did it do the thing?
Exactly. You wrote the fourth routine, you triggered the input, and you just observed the physical output. Did the robotic arm actuate? Did the telemetry radio broadcast a signal?
Right. It seems to work, therefore the code is good, let's ship it.
Yes. The standard was basically functional approximation, but as processors became infinitely more complex and clock speeds scaled from megahertz to gigahertz.
And now we're dealing with billions of operations a second.
Right. That macro-level observation became dangerously inadequate. The AI elevates the standard of what it means to be verified. Because the AI can process the microscopic details instantly, the fundamental question of verification completely shifts.
We no longer ask, does it seem to work?
No, we now ask, can we mathematically and physically prove, across millions of automated test iterations, that the silicon toggled the exact correct latches without a single undocumented side effect?
Wow, that is a massive paradigm shift. But it raises a really interesting dynamic regarding the human's role in all this.
What do you mean?
Well, does the AI actually make the technician's job easier by automating all that tedious hex reading? Or does it actually force the technician to work at a much higher, more rigorous cognitive level?
Oh, that's a brilliant question.
Because if the AI is constantly finding nanosecond timing anomalies that humans used to just ignore or chalk up to ghosts in the machine, the human now has to actually explain and resolve all those anomalies, right?
It undeniably elevates the cognitive load on the human. The technician is no longer acting as a human logic analyzer, just staring at waveforms. They're acting as a true systems architect.
Right, because the AI is just pointing out the what, not the why.
Exactly. When the AI surfaces a microscopic discrepancy, say, it proves mathematically that a specific register readback failed 0.01% of the time. The AI cannot tell you why it failed. It only highlights the mathematical deviation.
So the 72-year-old technician has to step in.
Yes. They must apply their decades of tacit knowledge to deduce the root cause. Is it a hidden flaw in the fourth compiler? Is it a hardware erratum causing a race condition on the memory bus? Is it a thermal threshold issue where the chip just got too hot?
The human declines the why, while the machine perfectly tracks the what. That is such a powerful synergy.
It really is. And this entire methodology, the documentation ground truth, the native hardware execution, the independent latch polling, and this human-AI symbiosis, it is all ultimately about building an architecture of absolute trust.
Because, as you said earlier, abstraction breeds complacency. We compile our code on our modern laptops, and we just blindly trust that 1,000 layers of hidden software libraries will accurately translate our intent into physical voltage.
And in most everyday scenarios, that's fine. But in high-stakes environments, that blind trust is a massive liability.
And that liability is compounding daily, isn't it? Look at the trajectory of commercial embedded systems right now. We are no longer just dealing with simple microcontrollers managing anti-lock brakes or municipal water valves.
No, the industry is moving incredibly fast. We are now embedding neural processing units, or NPUs, directly into the silicon to handle localized, on-device machine learning tasks.
We are exploring the dawn of quantum microcontrollers. The physical layer is rapidly becoming a black box of unimaginable complexity.
The more advanced the hardware becomes, the more opaque its physical behavior becomes to the programmer.
Exactly. We are moving toward an era where the hardware essentially abstracts itself.
And that's terrifying from a verification standpoint. If an NPU silently corrupts a weight in a neural network during a physical matrix multiplication, there will be no hard crash.
No error screen.
No, the system will simply degrade in its decision-making accuracy.
So, like, a self-driving car's object recognition confidence might drop by just 2%.
An entirely invisible failure, but with potentially fatal consequences.
Which makes this 50-year-old fourth language and its rigorous new test gate almost like a canary in the coal mine for the whole industry.
It really is. This team realized early on that you cannot verify modern silicon solely with software logic.
You have to interrogate the physical reality of the chip, using its native tools, and cross-reference it against an ironclad mathematical contract of intent.
They are establishing a brand new paradigm. The candidate test gate proves that rigorous, uncompromising bare metal verification is still possible, provided you are willing to break the assumptions of the PC software sandbox and truly embrace the brutal physics of the processor.
You combine the deep, historical intuition of human engineering with the relentless, granular pattern recognition of modern AI to force the silicon to prove its own fidelity.
It's the only way forward.
Think about the profound implications of that as we wrap up this deep dive. I mean, we had to build a high-speed, hyper-specialized artificial intelligence just to help a human expert verify that a relatively straightforward 50-year-old programming language correctly toggled microscopic latches on a physical chip.
It's humbling, really.
It is. So as we rapidly approach a future governed by opaque neural processors, infinitely complex silicon architectures, and hardware that literally learns and rewires itself on the fly, what kind of unimaginable, extreme partnerships will we have to invent tomorrow just to prove that the machines running our world actually did what we told them to do?
The chasm between human intent and physical execution is widening every day. Bridging it will require verification systems that are just as complex, if not more so, as the hardware they are testing.
And as that complexity continues to scale, we'll be right here to keep diving into the physical reality beneath the code.